Okay, this is the follow-up lesson to the derivative, and I'm using a language called LaTeX, which is very helpful in writing mathematics and then generating PDF presentation for them. And so last time we talked about the derivative as a limit, and in particular this limit, and we're going to use this limit definition of the derivative and try to compute some examples. And so for example, if you have a function x squared and I want to find the derivative function for it by using this limit definition. And so to evaluate this limit definition, I evaluate this expression inside the function. And so I get x plus h squared minus x squared, which is f of x. And then we talked about doing these limits a while ago, and the way we evaluate these limits is to simplify the top expressions and see if we can cancel the h. So if I multiply this all out, I get this expression, and notice the x squared will cancel, and so I get this. And there are there's an h here and also an h there that I can factor out, and if I factor out, I can cancel the two h's. And when h goes to 0, this expression becomes 2x. And we'll remember this example is going to come up a little bit later again. So if you have function x squared, then the derivative function, which is doing this limit, give us 2x. Now in the last lecture we talked about this function x squared and finding the tangent line to the function at the point 1, 1. So how do we find this equation of the tangent line? Well, in the previous example, the derivative function we found to be 2x. And so we want to find the slope of the tangent line. You plug in x is 1 into the f prime function. So when x is 1, f prime is 2. That means the slope of the tangent line is 2. And since the line goes to the point 1, 1 and has slope 2, then the tangent line equation, as we saw in the previous lecture, is y is 2x minus 1. So that confirms that example earlier. Here's another example. What if you have the function 1 over x? Again, by using the limit definition, I can evaluate this derivative function. I take this expression, put it in the function f of x. I get this. To simplify the top, we combine by using common denominators. And so the common denominator for this expression is x plus h times x. And if I do that, then I get this expression on top. And I notice that the x's will cancel. So I cancel that x. And I have a minus h on top. And then the bottom simplified to be like this. I cancel the h's. And I get this expression. And when h goes to 0, then I get minus 1 over x squared. Again, we'll remember this function and its derivative for later. Okay, here's some properties of the derivative. If you have a sum of two functions and you want to differentiate it, you can differentiate the functions separately, then add them. Similarly, if I was to differentiate a difference of two functions, I can differentiate them separately, then subtract them. And if I have a constant c multiplied by a function and I want to differentiate it, I can differentiate the function, then multiply by c later. And so using these properties, we can differentiate a lot more functions. Finally, here's the power rule. The power rule says that if I have a function which is a power x to n, where n is any real number, then the derivative is take the n, bring it down, and then subtracting the exponent by 1. That will be the new exponent. So the proof of this, actually, we have to go through the whole limit definition, but we won't go through that in this lecture. Let's do some examples. So earlier we did this example x squared, and we found that by using the limit definition we got 2x. Well, how do we do this using the power rule, which is a lot faster? Again, I take the 2, bring it down, and subtract 1 on top. And so I get 2x, just like we had earlier when we did it the long way by using the limit definition of the derivative. Again, earlier we did this example, and it was 1 over x, and we did it the long way and we got minus 1 over x squared. Well, how do we do it using the power rule? First we rewrite this as x to the minus 1 so that it is a power. Then to differentiate, we take the minus 1, you bring it down, and then subtracting 1 here gives us minus 2. And rewriting this gives us minus 1 over x squared. Again, that's what we got earlier when we did this the long way by using the limit definition of the derivative. Now we have, what if you have a bunch of functions added and subtracted together? Well, again, the 3 can come down to make this 15. Subtracting 1 gives you a 2. The 2 comes down to make this a 14. Subtracting 1 gives you a 1. There's a 1 here. When it comes down, it doesn't change the 8. Subtracting 1 gives you 0, and so that's gone. And because this thing has no x, it's essentially x to the 0 power. When you bring the 0 down, you get a 0 here, so this thing is gone. So again, 15x squared plus 14x minus 8. That's the derivative function if we were to use the power rule along with all of the sum and difference properties of the limit that we saw earlier. And that's the end of the lesson. Actually, I have another example here. What do you have something a little bit more complicated here? Well, again, just like before, we recognize this to be a power if we rewrite this as x to the minus 1/2. Again, bring down the power, minus 1/2. Subtracting 1 gives us minus 3/2. And rewriting this will give us this. That's the end of the lesson. Please go to the webwork page to finish your homework. I just want to say to the teachers who are reading this, normally I wouldn't go this fast on a lecture, but I just want to show the technology and not so much the content of the lecture. Okay, thank you.